Okay, so at Containerization Masterclass, we're going to have some fun playing with devices in containers here. So why is Steam? So Steam is a native Linux app. They've had one since I think when was it first on Linux? 2012, I want to say, something like that. And when they first brought it on, they were trying to only sell and ship Linux native games, and that was kind of a disaster. They tried like bringing Steam machines to the market and bringing developers to Linux. That didn't work. It was a massive flop. But sometimes really successful companies can have flops, and that's okay. It presents really interesting technical opportunities. So we get to play with things like graphics. We get to use the GPU, and this is really interesting because obviously AI is really big right now. So being able to access the GPU inside of a container, which a lot of people already know how to do, but a lot of people don't, is really useful. Audio, that's something that I guess Balena is already kind of familiar with. We have the Balena sound application, and we have the audio block. But this will also demonstrate one way to do that. Compositing, so we're going to be using Wayland to do windowing and compositing for Steam. And then also, we're going to be doing a few of these things in different containers, right? So we're going to be doing IPC across containers. Then, of course, we have input and storage. Storage is the easiest one, so let's start with that. Like I said, the easiest thing is storage. We all know how to do that. You map a volume into a container. Here, Steam kind of keeps things easy. Everything gets deposited in the home directory, so that's all we have to do. Create a volume, and then we map that to the home directory. Simple. Steam is then going to download all the files and put it there, and any games as well are going to be downloaded there. Any sort of compatibility tools, any sort of shaders that are compiled, that's all stuck in the home directory. Simple, done. How do we access devices? That's a little bit more difficult. So the classic like Unix philosophy, everything's a file. That really applies here. Devices are files. In actuality, not everything is a file, like network devices. Those don't map very plainly to the file like metaphor. It's not a good interface for that, but like basically everything else is a file. Like GPUs and input devices and sound devices, all of that is a file for our purposes. So what is a device file? It's a special file type, typically either block or character. I'm actually not aware of another type of device. It's just block or character. In operating on a file, device file, communicates in some way directly with the hardware. And you use system calls like open, read, write, and ioctl for IOCPL. Current developers typically say ioctl. And then you do operations on those files. Operations are mapped to specific drivers with what the kernel knows as major and minor numbers. Majors are kind of predetermined, and then minors depend on the device. So like, if you have a block device of a certain type, it starts at 1, and then increases as you plug in like more block devices. Like say a USB mapped storage device, that's going to increment that minor. And that maps to a specific device. So this graph kind of illustrates that. It's a little bit clumsy, I made it myself. But essentially you have the kernel and kernel space, then you have system calls, and the system calls operate on files, and then at the bottom you have the files that those system calls interact with. So we take a look at my laptop here, instead of the dev directory, you can see I've got a lot of files, and this is not unique. Linux just creates a lot of files. Whenever you're dealing with like a teletype terminal, or like I said, a sound device, or serial console, I mean, there's a lot there. That's all contained inside of the dev directory. And if we look at what's inside of the containers dev directory, it's a little bit more sparse. This is intentional. Docker only puts what's necessary inside of that dev directory by default, but of course we want more. So what's the difference between these? On my laptop, you'll see a dev tmpfs mounted, and in my container, it's just tmpfs. So TMPFS is just a memory-backed, basically file system. It's kind of a virtual file system. It's not backed by a block device. Dead TMPFS is actually a special file system the kernel will automatically create device nodes inside of as devices are probed or enumerated. So there's basically 5 approaches to getting a device node inside of a container that you want to use. I have seen people bind mount the host dev directory inside a container. Never do that, and I'll explain why. You can run a container privileged. That also brings in more device nodes, and I'll talk about that. There's also compose directives for devices and group add for privileges, and that's pretty handy. That's a good way to go. Make node, which is pretty handy in some situations. And of course, like I mentioned, you can actually mount a new dev TMPFS inside of your container, which is handy in some situations. So let's talk about those options. Bind mounting the host dev directory is bad because there are certain, there's kernel state that's unique to the execution context in some ways. Like when you open a terminal window, that actually talks to specific devices inside of your dev directory. And if you sort of duplicate that by bind mounting that directory inside of your container expects its own context. You can actually cause problems with your host system by doing that. Like if you delete then a device file inside of that container, it gets removed from the host as well. Then the host can't use it. You can corrupt like terminal context, which can make your host system break until you reboot. Very bad. Like don't bind mount dev inside of your container. A note that I put here is that it kind of breaks the implicit promise of containerization, which is that everything is separate. And I kind of already explained that, but like bind mounting it breaks that promise. You should never be able to break the host system by running a container, and that's exactly what bind mounting that allows. So the next option is privilege. I know a lot of people run containers this way. Try not to. It certainly is an option if nothing else works. There are vanishingly few cases where you need to run a container privileged. Unless you're getting like DRM master with graphics, like running a compositor, it's not necessary. You can do it with more fine-grained permissions than privileged. Some other sort of things to keep in mind is that running a container privileged doesn't update device nodes inside the container. That is, if you plug in a thumb drive or another disk, it will not update the device nodes inside that container. Likewise, if you start up a container, that container gets a copy of all the device nodes inside the host at startup, right? So if you unplug a device, it doesn't remove that device node anymore. The kernel just gets confused and doesn't allow operation from that device node if the device is gone. So privilege has limitations. If you expect to do any sort of hot plugging, it's probably not going to work for you. It also has issues with security because you are just passing in all the devices that were on the host when it started up. If you expect to run any services that may be vulnerable, say any sort of C program, like there's many C programs that have CVEs. If that's exposed to the network, you can then have issues with that service being compromised and then that container getting access to all of your host devices. So it's not ideal if you don't need it. Pretty much all these options mount a TMPFS on container startup. The compose directive is nice because it only copies in the device nodes that you specify in the compose file. And I'll show some examples of that so you kind of get an idea of what I'm talking about. This again has a limitation, there's no hot plug support. And another limitation that I've run into before where if you specify a device in your compose file that doesn't exist when the container starts up, the container can't start. So specifically, I run into this with testing when running virtualized. One device file that we're interested in is KVM, which allows us to run containers, virtual machines accelerated. The problem is if you have hardware that you try to run this on, it doesn't have the KVM file because it doesn't support hardware accelerated virtualization, the container won't start at all. So this solution doesn't work. You're basically stuck with either acceleration for everything or acceleration for nothing. Like you have to just turn off blanket. It's not good. One of the nice things about this approach is that you're not always running as a privileged user. You can specify group add and run as a non-privileged user, not root. And then you can basically give access for a specific group to your user to access devices that's more fine-grained. So it's much more secure. I recommend this for 99% of use cases. Do this unless it doesn't work. Thank you. So here's an example. We're not roll. Here's an example of compose directives. I'm sure most of you have done something like this. We map in the dev VRA directory here. So all the devices in this directory then will be passed into the container. And then I did group add video because the devices inside this directory are owned by the video group. So this gives the user permission to access those devices. Make note, this is really handy in specific circumstances. Specifically, if you're creating student devices at runtime, like KVM, what I talked about just a minute ago, this was a great solution here because the major number is static, and the minor number kind of gets in a little bit of what the Linux kernel calls missed character devices. But the minor number is dynamically allocated, and we can actually check the proc file system at /proc/minor at runtime to see if this module is loaded and if we can actually use this device. And if we can just create it with make node with the right permissions and use it inside of our container. We don't actually need to tell Docker anything. This, again, doesn't support hot plug. You can, if you know the major and minor, make the device node yourself, but you have to know in advance, so it's a little bit tricky there. It works for things like KVM time. And then the only limitation on this is you need either device secret rules or the make node capability, which is, again, much more fine-grained than Capsys admin or privilege. So here's an example of that. We have device secret rules in this compose file. And this has very specific syntax. It starts with the type of device. Here we have block, and character. The major number, so 7 here, which corresponds to loop devices. Ignore the comment there, I mixed up in the back, which is a different term. But so 7 is loop device, and then all minors, and then we have the permission to read, modify, and write. So this is the entry script, and this basically just checks procmess and says, do we have it? And if we do, go ahead and create it. This is actually used in the Wayland worker, but in essence, what this does is, if the hardware supports it, the module's loaded, we can use it, we can create the device node, and it works like any other hardware. Otherwise, you can bail out the message. Thank you. It actually looks a lot better. Otherwise, we bail out the message, or if we can, we fall back. For example, in the case with KVM, we don't have KVM, we just disable it, and it works fine. It's just slower. So the last option is dev CamPFS. What's nice about this is it mirrors how the host system works. And there are some benefits of this uber privilege. This is actually how balena images work. When you run them privileged, which you don't need to do actually, you can just have Capsys admin, which gives you enough privileges. It's a little more complicated to set up. You actually have to do some move mounts and things like that in order to get a full dev CamPFS. But the plus side is if you need dynamic access hot plug to devices at runtime, if you plug something in and you need that to show up in your container, this is your only option. So it's really handy to have. It also does provide full access to all devices on the host, so there are some security implications to that. But with these being regular files, if you want to be more secure, you can simply delete the ones you don't ever want to access, and that kind of solves it. Yeah, that's it.
Yeah. How is Capsys admin like more secure than privilege?
Great question. So they're very similar. Capsys admin gives the user inside the container a lot of privileges. Okay, so it's not like it's much more secure than privilege. There's minor differences. So Capsys admin does not, by default, pass in all devices, but it does give the user running the container all the privileges they would need to do so. You know, like mounting a dev KPFS. If you have mount access, you can do this, and you can get access anyway. What I recommend is if you have to do something like this, run any untrusted programs or anything that needs to have network access as a lower privileged user. So drop those capabilities, right? So set up anything you need to inside your container. For example, your dev TPFS. Delete any device nodes that you may not need, especially block devices, because if you have access to block devices, you can mount file systems, you can tamper with the disk, you can do all sorts of things. You can basically escape the container in 1,000 different ways. Restrict access, then drop privileges to a lower user count before running any services. If it's not exposed to the network, it's probably not that big of a deal. You should be running code you know anyway. Here's kind of an example of what that looks like, and I didn't come up with a snippet. I mean, I think I physically typed it, but this is kind of copied from a script that's already in our balena images. It essentially creates a new mount point at PNP dev. We mount a dev TPFS there. That's what that looks like. And you can actually mount any number of these anywhere you want. It doesn't matter. It's just by convention, it's mounted at /dev. Then we move the devices that Docker created itself to that new dev TPFS. That includes console, obviously that MQ and SHM, which are basically ITC mechanisms. PTS, pseudo terminal file system. We move those to the dev TPFS unmount dev, and then we move the mount of the new dev to /dev, and there you have it. I don't ever do this manually. I copy a snippet. It would be really nice to figure out how to expose users to this without balena lib, but it's not that complicated. So we know how to pass devices in. How do we know what devices we need? I mean, if you're not a Linux expert, you don't know the deep details of the DRM subsystem and audio and things like that. Or say you want to map a you want to map a disk image to a virtual disk and map partitions. How do you do that? Well, just ask. This actually works for NVIDIA too. Even though they have no interest in standards or doing things the Linux way, their stuff is very closed. The user space libraries are closed source. You actually can just run an NVIDIA program, or rather a graphics application that uses NVIDIA libraries, and it'll tell you if you grep for a dev what device is this trying to open, and then you just pass those into your containers. It doesn't matter. Everything is a file. All devices are files. You can just run strace. I might have missed saying that. strace traces system calls. So if you run strace in a program, it'll tell you what device it's trying to open. You can just grep for dev, and it'll show you. So at the top there, it's trying to open card 1.8 for whatever reason. It doesn't exist. Down towards the bottom here, you'll see it's opening dev DRA, and there's two different cards there. It tries to open and succeeds. Those are the ones we need to pass in. So we just need dev DRA for this GLX years example. Does anybody here know what Mesa does? Nice. Well, put your hand down. I know you know.
I don't know.
Okay, cool. So Mesa is very useful. Basically, it implements graphics APIs. I'm sure a lot of you have heard of OpenGL. Maybe some of you have heard of OpenCL. Everybody here has heard of CUDA. That's not Mesa, but it's an analogous concept. libcl, similar. That's compute API, right? So these have to come from somewhere, and Mesa is the open source implementation of these APIs, okay? If you have an application that uses any of these, you need Mesa or NVIDIA's libraries. And what Mesa actually does is, on the back end, it talks to these device files, it actually opens them and does operations on them, implement these APIs. So for example, when you call a function in OpenGL to create graphics context or form some state operation for OpenGL. It will do IOCLs, or IOCTLs, on a device file to do things like queue up graphics operations or manage graphics buffers. And you don't need to be able to do any of those things. Mesa will do them for you. All you have to do is pass in the relevant devices. And once those are in your container, Mesa just works. But if you're doing any sort of rendering, you do need Mesa inside of your Mesa or NVIDIA's libraries inside of your container. So let's try it. How do we run a simple compute example inside of a container? It can't get much more simpler than this. We are simply mapping in the DRI directory. Those are the devices we talked about. And then this is a container I pre-built with an OpenCL like benchmark. It's called CLpeak. And this just basically runs some benchmarks through OpenCL on the GPU. And it works. All we did is pass those devices, and it starts running a benchmark in a container. You can see me frantically trying to kill this at the bottom because it makes my laptop unresponsive for minutes at a time. But it did work. It actually is using the GPU. So it's really, really simple to run something that uses graphic hardware. It's not magic. But then what about something graphical? Because that was just crunching some numbers, right? Yeah. So here, we're trying to run ES2 Gears Wayland, and that's a hint right there, the Wayland part. And we get an error. The XG runtime directory isn't set, and it fails to initialize the display. So what's going on here is that application wants to open a window, right? The trouble is, we don't have any access to what's known as compositor or display server to be able to open that window. We can connect to the GPU and crunch some numbers, but we can't actually open a window to show anything interesting. Beyond just opening windows, the compositor, or if you're using X, the display server, handles things like input and events. So for example, if you close a window, that will also send an event to the application to say, hey, you're dead now. So what we need to do here is map in the volume that the Wayland socket is contained in. So by convention, it's in run, and then the XG runtime directory, that's by convention, run user, and then user ID. Once we specify those two things, this containerized application can then open a window on my host Wayland compositor, right? So my laptop is running Wayland compositor already, and I just see those two things, basically tell it where it is, and there's my application running. That then raises the question, okay, how do I containerize the compositor? Because on balenaOS, I don't have it already running, right? So it's not terribly hard. You can set this up as a separate service, and I encourage that for a number of reasons. When you separate things like this out into different services, it makes them download and run quicker. You can modify this service and upgrade it more easily without taking down the rest of your application stack. And all you really have to do is set up interprocess communication to handle this. It does need access to the DRM nodes, right? It does need to be able to grab DRM master. On balenaOS, this is not terribly hard. You do need to stop the splash screen program. What is it called? I forget. Playback, that's what it is. Thank you. You do need to stop playback, which you can do with dbus. Go figure more IPC. You do need Mesa or NVIDIA libraries, right? Because you're actually doing rendering. And the way that works is that an application will render to a buffer, and then the compositor maps that to a texture, and it does cool, fancy graphical things like, like in macOS, when you move your mouse to the top left, it does the expose thing. That's all compositing, right? So that's actually a graphical program that is compositing those separate images together. That's why you need those libraries with Wayland. With X, you really don't need that in the same container. It's all in your application container. X doesn't really do compositing, but if you run a compositor, you would then need that. With X, it's kind of separate. It's messy and there's a lot of historical value there. So what you do need as well, then is a shared volume for that socket, just like on my laptop in the last slide. And then what's cool too is if you run a Wayland compositor, you can be compatible with X applications. There is a part of the specification that specifies something called X Wayland, so you can actually be backwards compatible with X programs that expect to talk X11. And if you just run it with like the X Wayland flag, it'll create basically an X server on top of Wayland with a socket that X programs can connect to. You do then need a separate volume that's shared for that socket that's in PNP. So it's as simple as this for running a compositor. Again, you need those device nodes, you need the volumes that are shared, you need to set XCG runtime directory, and that's about it. You can then run like an outline container with the Wayland compositor, and it's pretty simple. So what about audio? Audio is pretty similar to graphics, go figure. The device files are in a separate directory, /dev/sound. That's convention by Advanced Linux Sound Architecture, or ALSA. ALSA only allows basically one client at a time, though. It's kind of similar to with graphics, having VRAM master. So there are some sound servers that exist, namely Pulse Audio and Pipewire, that allow for sound mixing. So you can have multiple clients connected to the sound server, and then that sound server will do things like allow you to combine streams or alter the volume of different streams independently. So it's really nice to have. And it works the exact same way as the compositor. You run that server, you have a socket the clients connect to, and you need to make sure that that server has access to the hardware information. So Pulse Audio, very, very similar. You map the devices in. Pulse Audio will also use shared memory, so that's what the IPC host is for. And then we add the audio group, map in the volume, and it's very, very similar to graphics. So how does UDEV fit in all this? It used to be that UDEV was actually, as far as I know, used to create device nodes before DevTMPFS was merged into the upstream kernel. Right? So UDEV actually talks to the kernel, gets events from the kernel over that link socket, and then nowadays does special handling of devices. Like if you have a device that gets enumerated and creates a device file that isn't a constant name, UDEV can be used to handle that device in such a way that it creates a symlink to a persistent name, so it's always the same name. That's really handy for disks and things like that that might be enumerated in different orders. So you have like SDA, SDB, and SDC. Those have no guarantee as far as what name they're going to end up with on boot. It's kind of a race, right? Because it's all asynchronous. So UDEV, one of the things that it does modern times is it will actually create persistent links for those. But before DevTMPFS was a thing, it would actually be used, as far as I know, to create all device nodes. Xorg also will use UDEV to be notified of input devices, and I think Pulse Audio also has a backend that allows for that, but it's not necessary for most use cases. If you need hot plug, most of the time you're fine with just DevTMPFS. You don't need much more than that. And you can also run UDEV containerize. You can run it in a separate container. It really depends what you're doing. But most of the time, you don't need it. So I guess that's the demo thing. And then also the code for this, after I run the demo, you can find on my personal GitHub. It's going to be under Balena's team. And there's no README currently, but you can download it, run it, play with it. I don't have anything to amplify. I don't have a, that's what I want, this one. Oh, that's microphone. Is it muted? Oh, it's trying to play through the.
Oh, is it?
The HDMI. That's not
Do you have any sound?
I spent a lot of time on it too.
Can confirm it works.
So this is balenaOS. It's running actually in a VM on my machine. It's booting. Give it a minute.
The demo gods don't like you.
So this is the compositor running right now. And there's Steam. Oh, there it goes. Cool.
That's the sound.
It's got audio.
Hooray.
Woo!
And I'm going to remind you, this is really crazy, okay? There's a whole nother layer here of the virtual machine that is doing auxiliary graphics through the container, through the virtual machine, on my not gaming laptop.
Question.
No.
Okay.
What?
So if you plug in like a joypad, joystick stuff, it's gonna detect it. You have it set up like.
I could easily make that work. I'm not that good.
It's a matter of like just mounting the device.
Sorry about the mess. I've really let the place go since you came to me. By the way, thanks for that.